We're very happy to have Nir Lazarovich, who's going to tell us about cat zero cube complex.
Hey, thanks, Mark. Yeah, so I actually meant this. I can point out people that already know the stuff and should not be in this room, but the reason I wrote this is for everyone else to feel free to ask questions. Don't let the nodding crowd at the back. They're probably doing work on their computer. Sorry from actually asking questions, okay? Yeah, so the plan is we need to cover the basics of what are cat zero cube complexes. And then in the second talk, we'll talk about how to construct such things. And then special cube complexes, and the last talk will be about groups acting on products of trees. Yeah, so let's start with the basics. So CCC, which apparently is also the Canadian Commercial Corporation. So yeah, if you Google CCC, you will not get results in cat zero cube complexes. But yeah, so here's the definition of cat zero. So geodesic metric space is cat zero if whenever I take 3 points in my space, okay, can form the geodesic triangles, right? I mean, my space is geodesic. I can connect any 2 points with the geodesic. And what I can also do is I can look at the space, the Euclidean space, and form a triangle which has the same side length as this geodesic triangle. So this is called the comparison triangle. So x hat, y hat, z hat. It's unique up to the isometries of E2, so we shouldn't worry about this. And what is the condition? The condition is that whenever I take 2 points here on this triangle, let's say P and Q, then I can form I can choose points on this triangle, right, that have the same distance from x hat. Okay, so this will be maybe P hat and Q hat. And the condition is that the distances here are shorter than the distances in the comparison triangle. Okay, so this workshop is about combinatorial. What was the title? Cat cube complexes and
Combinatorial geometry.
Combinatorial geometry. So this is not combinatorial. This is actual metric geometry. Okay, but one can sort of also do a coarse version of this, which we'll use at some point, which is hyperbolic. So maybe let me just say and not write. What does it mean for a geodesic metric space to be hyperbolic? So instead of comparing it to the Euclidean plane, maybe you want to compare it to H2 or to a tree. Okay, and instead of having a strict inequality like this, you put a plus some error term. Okay, so those two things were introduced by Gromov, or at least the naming is by Gromov. And for how many of you is this the first time you see cat zero? Okay, good. Excellent. So let's see some examples. So cat does not stand for the animal, it stands for Kartan, Alexandrov, and Toponogov. Attribute of Gromov to those three. And let's see examples. So the examples are really going to be, let's say, exercises. I'm not going to say much about them. So maybe the first example is just the Euclidean space plane, you know, En. Yeah, this is Rn with the Euclidean metric. Okay, this is quite clear, right? I mean, the comparison triangle is basically the same as the triangle in our space, especially in E2. And so you get an equality and not an inequality. Okay. Maybe the next example is hyperbolic plane. I'm not going to say much more about this, but again, the idea is that the triangles in this space are thinner than Euclidean space. And we all know we draw triangles in hyperbolic space like this, and they look thinner. Does this mean that they're actually thinner? No, you have to prove something. Okay. Here's an example that will be important for us. Trees. Right, so something like this. is hyperbolic. Let's just see this. It's an exercise. Yeah, so I take 3 points here. What does the geodesic triangle look like? Well, it's actually very, very thin, right? Okay, so the distance between 2 points here is basically 0, right, up to a certain distance. So it's definitely going to be smaller than the Euclidean. Okay, and what else can we do? We can form products. Okay, note the last talk will be about product of trees, so it's already interesting enough to spend the whole talk about product of such things. We can take convex subspaces, etc. Okay, you can also give non-examples. Yeah, so what would be a good non-example? Maybe the sphere. Sphere, all points of distance 1 from the origin in R3. That's not ket 0. Actually, also S1 is not ket 0. But we want to think of it as ket 0. We'll see later what we mean by that. But yeah, what happens in the sphere? In the sphere, the should not do that. We don't have Danny to yell, basically. So triangles in the sphere are actually quite fat, right? So how a triangle would look like. It's definitely not thinner than the Euclidean triangle. And you should believe that if you took ever a plane and you believe that Earth is round. Okay. What else, which again will be important for us? Maybe if you take a cube, but you only take the 2 skeleton of the cube. Okay, the 2 skeleton. That puts this. Okay. Skeleton of the cube. That's another example of something that's not ket 0. Okay. And here's a bunch of exercises that will be useful for us later. So maybe the first exercise is that ket 0 space has unique geodesics. Unique geodesics. Okay, this is, I mean, for instance, if you want to prove that S2 is not ket 0, you can note that from the between the 2 antipodal points, there are more than 1 geodesic. Right? And the same works for S1. We'll see S1 also S2 fails also because of this property. A ket 0 space is contractible. Okay. And another exercise. I did I put the exercise actually on it? Yeah, maybe a generalization of. Okay. If I have a ket 0 space and I have a map from Y to X, which is a local isometry, then it is in fact an isometry. Isometric embedding. Isometric embedding. Okay. Maybe one last thing, might be more difficult. If I have a finite group of isometries acting on X, then G has a fixed point. Yeah, all actions will be by isometries. Questions? Okay. Good. The next definition is we want the local version of this. Okay, so geodesic metric space is non-positively curved if it is locally ket 0, meaning every point has a neighborhood such that when you restrict your metric to this neighborhood, it is ket 0. Yeah, some people just call it locally cat zero. It's fine. We use non-positive curvature. Okay, and here is the remarkable theorem. Really put Gromov, but for Riemannian manifold, this was proved before, and it says that if X is geodesic, that complete as well, when it's complete, cat zero, non-positively curved, and simply connected, then X is cat zero. Okay, so what does it tell you? It tells you that by checking a local condition, okay, and some relatively mild global condition, we can actually get this global metric condition that gives us all those nice properties. And in particular, see, if you only care about topology, you should still care about this theorem because it tells you that you only need to check this local thing and simple connectivity to get contractibility, for instance, right? It's quite strong. Okay. We will not prove this theorem. Treat it as is. And now we are really ready for the what we are here for, which are cat zero cube complexes. Any questions about cat zero? Okay. So a cube complex is a complex obtained by gluing together unit cubes of cubes, right, of various dimensions. By, how did I even know how to phrase it so that it has only one meaning? By isometries of faces. Okay, so it's this sentence, right? Let's give examples. Okay, so the example you should think of is maybe a graph, yeah, or a tree is a cube complex. Note that I allow you to take, for example, an edge and glue the two endpoints, right? This is a legitimate. So this is a legitimate cube complex for me. Okay, so graphs. Just draw some graph. Okay. But actually, we don't have to restrict to one dimension. We can go up in dimension. So here I can, for instance, glue a square onto this graph, or maybe glue even higher cells. Attach maybe a cube. Okay, so and so on. Tell me when to stop. Of course, we can have more than one thing here. You can really go forever. Okay, so those are the, I should not write examples. And, well, okay, you know what's coming, right? Cat zero cube complex. Okay, so this for me will be CCC, no one. Is a cube complex whose induced metric is cat zero. What does it mean, this induced metric? You just put the Euclidean metric on each one of them. Okay, and use the gluing to now define metric on the whole thing. So if I want to measure the distance between a point here and a point here, I just need to check all the possible paths I can do, or if you want jumps from one point to the other and minimize this, right? Yeah, I seem not pleased with this. Okay. Okay, and we say that it's non-positively curved cube complex is, well, you can fill in this. So, but let me just put so I'll use NPCCC for those. Okay. Great. I know that I told you already that to check that something is cat zero, or check that something is cat zero, you only need to check something local. Okay, and here, since the space is made out of cubes, of course, I don't have to check this local condition inside the cubes, in a sense, right? So really where the whole thing happens is at the vertices. So for this, maybe we want to define the link. Wait, I have examples before that. I did not. Let's do at least 2 examples. Yeah. Cat zero cube complexes. So we saw one already, right? Maybe trees, right? They're both cat zero, we saw, and cube complexes. Cat zero cube complexes. Maybe another example is you can take the Euclidean plane and tile it with squares. When you look at the induced metric, the space, you get back the metric on the Euclidean plane. So again, it's cat zero and the cube complex. And products and so on. But really we'll get much more once we learn about the link condition. Yeah, so the definition of a link. So the link of a vertex V in this cube complex is what do I want to write? A small sphere around this vertex. Yeah, this is a terrible. If anyone saw the actual definition of link, this is a terrible definition, but this is what we actually think of. So let me just do the drawing. Maybe let's use. Can I use this drawing? Let's see. So if you pick this vertex, for instance, my vertex V, what I want to do is I want to draw a small sphere in this metric space around V and claim this is sort of the link. So what will we have? We'll have one point on this edge. So green. This, you see green. Okay, so I have one point on this edge. Okay, here we see a whole sort of what do you call those things? An arc, right? In this square, and here we'll see maybe some, I don't know, spherical, like this, a triangle. Okay, so one can also define it combinatorially as, you know, all the cells that strictly contain V with the inclusions of the things. Okay, is this clear? So I mean, the link, once I can draw it here, it will be the following complex. Wait. We say that X satisfies the link condition. So this is supposed to be a condition to be locally cat zero, non-positively curved, if for every vertex, the link is simplicial and flagged. Okay, so it is a complex made out of simplices, and we ask this complex to actually be simplicial and to be flagged. So what does it mean to be flagged? It means that every click is the one skeleton of a simplex. And let's see examples of things that do not satisfy the link condition. Okay. So what does it mean not to satisfy the link condition? So for instance, you can take two squares or even one square and glue this to that. Right? This is the legitimate cube complex, but it doesn't satisfy the link condition, because if I look at the link of this vertex, what I'll see is this loop, and this is not simplicial, right? Okay, and similarly, I can take maybe two squares, glue them like this, and again, what I'll see around this vertex is a graph that's not simplicial. Yeah, coming from this and that. Okay, so it has to be simplicial. You don't want to glue squares in those ways, basically, and you want it to be flag. So what flag is supposed to prevent is exactly the example of the two skeleton of a cube, right? So if I take three squares and I glue them in this way, okay, so here I don't have the cube inside, it's just three squares, it's two-dimensional. Yeah. Then the link of this vertex is this triangle, so I see a click there, complete graph, but it's not the one skeleton of a simplex, so it's not filled. Okay. And what it sort of indicates is that there is a missing cube. So if it were filled, if it were flagged, then there would be the whole three-dimensional cube that we sort of see, should be seen in this picture. And here's the theorem, I guess, Bomo. That X is a cube complex, and X is non-positively curved if and only if X satisfies the link condition. Okay, so we know how to check that something is non-positively curved. It's just a combinatorial condition we have to check, and we also know how to check that something is ket zero. You just need to check this plus the global condition of being simply connected. Yeah. So now I can really give you some examples of ket zero cube complexes or non-positively curved cube complexes. Any questions? Okay. Yeah. So we already saw some. Maybe check what is the link in those examples and why it satisfies assumptions. But more examples. So I'm continuing this list. Yeah. So maybe also if you take a quotient of such a thing, so for instance, a graphs are non-positively curved cube complexes. If I take a quotient of this guy, so for instance, a torus, right? No, let's say squared, so it's this cube complex. This is non-positively curved. More examples, more interesting examples. Maybe you want to take the surface of genus 2 or higher genus. Okay, you can write it as the following gluing. Okay, and choose the following cubical structure on this. So all of those things to be vertices, but also add another vertex for each. Maybe I'll switch color. Was this allowed? This is not. Orange is good. Okay, and connect all of those vertices, maybe this one, to not all of them, all the ones in the middle of edges to the central. So one needs to sit down and check that it satisfies the link condition. But once you do that, you know that this guy is a non-positively curved complex. Of course, there are other ways of cubulating the surface. It's one of them. And maybe I should say, we want a cat zero cube complex corresponding to this. What can we do? We can pass to the universal cover, right? This will give us a cat zero cube complex. Maybe I just draw something. So, there's a cheat move here. The universal cover of the surface is H2, right? And you can tile it with squares, so that, well, okay, around this we see 8 squares. Around those vertices we'll see 4, and around those we'll see 8 again. So try and tile this. This is just the universal cover. Okay, next example, very important to us, will be the Salvetti complex of a right-angled outing group. So what's a right-angled outing group? Well, you take a graph, a simplicial graph, and you form the following groups. So I'll just call it reg of gamma. It's a group whose generators are the vertices of the graph. Okay, and two such generators commute if they're joined with an edge in the graph. Okay, so for instance, the free group is a reg, right? I can take the graph with no edges. So give me a free group. The group Z to the N is a reg. Take the clique. I can form all sorts of things this way. And what we can note is that this is the pi1 of the following complex. So what I'll do is I'll take one vertex. Okay. I'll put an edge for each one of the vertices of gamma. Okay, so each one of them is labeled with one of the generators, one of the vertices of gamma. And now I'll add the relations, right? So I have commutation relations between V and W if they're joined with an edge. Then what I'll do is I'll glue in a torus, right, to form those relations. Okay, but maybe this is not enough to get this. This is enough to get the pi1 to be this guy, right? As we all know from Van Kampen, but maybe it's not enough to satisfy the flag condition. So what you do is whenever you're sort of missing a cube, you should put the cube. So when are you missing a cube? Basically, whenever you have a higher clique in here, so U, V, W, then maybe you want to put a cube labeled U, V, and W. Yeah. So a 3 torus, you glue it into this picture. By doing all of those things, adding all of the higher dimensional cells that are needed, this will be a non-positively curved cube complex. And this is an exercise for you to check what is the link. And maybe another such example. Let's see, wait. Yeah. Another such example is the Davis complex. What's the Davis complex? Well, you follow a very similar Davis complex of a right-angled Coxeter group. Okay, so the right-angled Coxeter group is you take the reg and you mod out by V squared is 1 for all V. Okay, so you make all of those generators into involutions. And you can form a complex on which this guy acts. Yeah, maybe some caution. I cannot form a complex, right, that's non-positively curved and whose pi1 is this guy. Why is that? What? Yeah, we have those involutions, and we saw this exercise that tells us if you have a finite group acting on a cat zero space, it will have a fixed point, right? Okay, but the action of this group on the universal cover of what I'll build will be such, I mean, we'll have such a, well, should not have such a fixed point, and it will. Okay, so we cannot hope for that, but we can still hope for this to act on a cat zero cube complex. And the way you do that is you take the Cayley graph. So this is the Davis complex, maybe X of gamma, is you take the Cayley graph of this right-angled Coxeter group. with the standard generators, you crush, I mean, you have V squared, right? So you crush them into one edge, do that. So let me just treat this as the Kelly graph and glue cubes whenever possible, basically. So again, compute the link and show that this is a category cube complex on which gamma acts. I'll maybe leave it to the exercises. Okay, and now we're really ready for the good stuff. Why do we care so much about category cube complexes? So we'll see there are several reasons. First one is we want to build actions on cat-zero spaces. We saw they have all of those nice properties we want to have for our group that acts on those things. But the real reason is that they are very easy to construct. So this we'll see tomorrow. And the reason for that is that they have this very nice combinatorial structure coming from hyperplanes. Okay, so here's the definition. Yeah. So first of all, I need the notion of a mid-cube. So inside the cube, right? So a cube for me, unit cube is just 0, 1 to the n. I can find a mid-cube. What's a mid-cube? It's when you restrict one of the coordinates to be 1/2. Okay, and now a hyperplane will be oh yeah, they want to say. Let's take a cube complex and consider the space formed by sort of gluing all mid cubes according to X. You know? I'll draw the picture. But yeah, let's say this is my cat-zero space, my cube complex. Okay, so I have here 5 squares and maybe an edge. And what I do is I look at all mid cubes. So this is a mid cube. This I'm not allowed to use. This is a mid cube. Right? This is a mid cube, but I can glue it to the next one. Okay, and glue that, so on. Okay, so here really the space I'm thinking of is this point, and this long line has how many segments? 6 maybe. Yeah, but there are more, right? I have this guy, that's also a mid cube. I have this guy, that's also a mid cube, and so on. Okay, so all of those. So this is the space. It comes with an inclusion. Okay, want an immersion into this space, right? Obvious. And a hyperplane for me would just be a connected component of this space with its inclusion. So hyperplane is a connected component of this space. Okay, so again, this orange thing is a hyperplane. Yeah, I'm really thinking of it as this abstract thing on the side with sort of an embedding, an inclusion into it.
You specify a hyperplane by specifying a one cell based on it being perpendicular.
Right. You can also do that. This is actually how Micha Sagiv did it first. I mean, the point is you want to take the collection of edges that are closed under being parallel, right, in a cube. That's another way of seeing it. Right. And here's why they're so wonderful. So if H hat is a hyperplane of my non-positively curved cube complex, then this map is a local isometric embedding. That's great. We already heard this right? This will mean, by the way, that this H hat is itself a non-positively curved cube complex. Right? Note that mid cubes are cubes. Right? So it's formed by cubes and it will satisfy the non-positive curvature condition because locally it sits very nicely in X. So in particular, this means that this map is a pi1 injective map. Why is that? This goes back to the property that we talked about, one of the first exercises I gave you, which is that the universal cover of this is ket 0, universal cover of this is ket 0, and this map being a local isometric embedding becomes, when you lift it, becomes an isometric embedding. Okay, so in particular, yeah, if X is itself a ket 0 cube complex, then, well, it's simply connected, right? This becomes, I mean, this pi1 injectivity of this thing will tell you this must be simply connected. Okay, so it is itself ket 0. Okay, so is a ket 0 cube complex. This embedding is an embedding. And that's the most important thing, H separates X into two components. Meaning when you remove H hat from X, you get two connected components. Yeah.
Is it possible to say again the sentence that what you're green in the previous word?
What's, sorry, this?
Yeah, well, the green.
The green. The sentence about the green. Each one of, I mean, I was just drawing different hyperplanes. I ran out of colors because, well, someone told me not to use Outline. And no, but so I drew them here. So that's the space I'm considering here. I'm taking all mid cubes, and whenever they sort of share a face, I glue them together. Okay. And so this is what I get. This is the collection I get.
The green are the hyperplanes?
The greens. So each connected component here is a hyperplane. Right. And this is sort of you want the space of all hyperplanes.
Are the greens connected with the oranges?
Are
the greens connected with the oranges?
No, that's the space. Yeah. I have a point. I have a segment of length 6. I have 4 edges. They are not gluing according to X means if, again, I'll not really define it, but the point is if you have this mid cube, right? Ending in this is also a mid cube. It's a mid cube of this edge, right? Okay. And here I have another mid cube that meets this mid cube. I'll just join them together, glue them together.
So
abstractly here on the side, right? So this is, let's say this is edge number 1, this is edge number 2. I just take those mid cubes and I glue them together according to how they're glued in X. This is not a gluing in X, right? Right. So this is why I don't take whatever it is, 6, I guess, and sort of glue it to 1.
So the last component, which is vertical to 1, so that belongs to the
which one? The 6, you mean? No.
Yeah, that one. So does it belong to the hyperplane?
Yeah.
Okay.
Great. So you see there is some content into which one was it? The fact that it embeds, right? In a non-positively curved situation, it can also not embed. I can get a crossing here. So you know what's the exercise? The exercise is go over all of those examples and find all the hyperplanes. Yeah, you can do that. Or at least describe them, say something about them. Okay, so I leave this really as an exercise. kind of sketched most of what goes on here. 1 is really important. 2, 3, 4 follow from this. And this last fact, h hat separates x into 2 components. Let me just say something because it's so beautiful that you should all see it once in life, at least. If I have x is simply connected. Okay, so you just think of a topological space. I mean, and I have inside x, I have a subspace, say connected subspace. So A connected inside x, which has a neighborhood, a product neighborhood. Okay, so what does it mean? It means that if I look at a small neighborhood of A, basically looks like A times something like open neighborhood. Maybe I want to put this, whatever. I'm assuming kind of both, right? That I can embed both. So I'm not going to say more than that. But what's the conclusion? The conclusion is that A separates x into 2 components. Okay, and here's a hint. The hint is you can map the space x into S1 by mapping this interval -1, 1 to an interval that you grew here. So let me write S1. Yeah, maybe that's the hint. The hint is S1 is -1 up to 1, where you glue the endpoints. Okay, and think how simple connectivity is related to this map. Great, I leave it at that. Okay, so actually what we get here is not only that it embeds, it is two-sided. So two-sided just means exactly has this kind of property. The neighborhood of my hyperplane is a product neighborhood. Questions? Are you all trying to solve the exercise now? Okay, great. Yeah, so let's see. I mean, why is it so important to have those hyperplanes? So here's one instance of why it's important. We can define a metric using those hyperplanes. So the combinatorial metric. So here's a definition that does not use the hyperplanes. So X, let's say, is a Atelier cube complex. Let's denote by D1 the length metric or the graph metric, graph metric on the one skeleton of X. Okay. So if this is, for instance, a cube, a square, so in my X, previously the distance between this and that was maybe square root 2. Now it is 2, right? Yeah, well, D, maybe I should put D2. Okay, so that's a metric we really like, and especially if you came to this workshop, really like, because it's all about, what was it? Combinatorial geometry, right? Yeah. That's combinatorial geometry, right? I'll agree. Okay. So here's how we can use hyperplanes to express D1. Figured I missed something important. Of course I did. Okay, let's do it now. No, actually that's not good. So here's the lemma is that D1 VNW is just the number of hyperplanes separating V and W. Yeah, so here let's go back to this example. Here, how many hyperplanes do we see in the whole picture? I collect the colors of them. Okay, I have this mid cube. One. I have this mid cube. Another. Okay, and in this example, we see that V and W are actually separated by those, right? By each one of them. So in this case, those are all hyperplanes that separate V and W. That's the count. Yeah, is it clear what the lemma is saying? Let's prove the lemma. Until when did you start? When did you start? 32. Okay. Great. So let's prove the lemma. So there's one inequality that should be obvious. Each inequality is obvious. Maybe none of them is. I want to go from V to W, right? If I want to compute this, I have to, work out what are all paths and look at the minimal one from V to W. But what do I know about those paths? They have to cross VI. I mean, the hyperplane separates V and W. If you want to go from V to W, you have to cross a hyperplane, right? Each time you cross a hyperplane, you've used an edge, right? So this inequality is obvious, very clear. Yeah, are we all happy with this? So what could go wrong? What could go wrong is that maybe to go from V to W, you have to cross a hyperplane, maybe cross it back, and then cross it another time, or maybe cross a hyperplane that does not separate them, right? Could happen. So let's see that this does not happen. So what we really want to show, that each of the hyperplanes here separating V and W is crossed once. Okay, I mean, really, generally, what we want to show is that no hyperplane is crossed more than once. Right? This will also include the ones that do not separate V and W. If I had to cross a hyperplane that does not separate V and W, so let's say I have a hyperplane here, and my path, my minimal path did that. Right? If I have to cross it once, I have to cross it twice, right? Because I have to come back to the same side I started with.
Still assuming X here, X is captured.
X is, yeah. Okay. So really, this is what we worry about, right? I mean, that's a picture, or maybe that's a picture we worry about. But really, we want to show that every hyperplane, to show that each hyperplane is crossed at most once. Yeah, those must be crossed, so we'll get with those, but the ones that do not separate V and W, you have to cross twice at least, so it will not be. Yeah, so why is that? Okay, the idea is that we can do some kind of an inductive argument to show that this does not happen. Yeah, so let's assume that we're in such a situation. Okay, a hyperplane is crossed more than once. Let me actually reproduce this. So here's my hyperplane. Okay, and I cross it more than once. So here's V, and I cross it again. And let me assume that this is sort of the shortest interval in this path that I see that on its two ends is crossed by the same hyperplane. Okay, so in particular, I will not see something like this, right? Let me see a shorter interval. Yeah, this was supposed to be the interval. Sorry. I'm assuming this interval is the shortest, such that in its two endpoints, I see the same hyperplane being crossed. Okay, so this is not shortest. Yeah, you can find the picture. I'm looking at paths from V to W. I'm actually looking at the geodesic between V and W, so the shortest path. Okay, and I assume contradiction that some hyperplane is crossed more than once. Okay, so the orange line here is supposed to represent the hyperplane that's crossed more than once. And what I assume in this path, I have such a hyperplane, I can assume that I look at the subpath that is minimal with respect to this property. So subpath such that on the two edges on its end is crossed by hyperplane, and in the middle, every hyperplane that crosses it once. That's the. Okay. So what do we know about this edge here? Maybe let's separate into two cases. One case is that the path has length 2. And in this case, what do I actually see here? Well, what I see is backtracking. I'm just going along an edge. If I cross again this hyperplane starting from this vertex, it must be because I walked back on the same edge. So backtracking, and it means that I can reduce the length of the path, right? This was V, this was W, and now I can form the new path, which is just do this. Remove the greens. Okay. What happens in this case where I have actually more edges here? Well, note that each one of those edges is perpendicular to some. Do I have more colors? I do have more colors. Oh. Perpendicular to some other hyperplane, right? And what do I know about this hyperplane? Well, it must separate this edge from this edge, right? If not, then it would have to cross this path again. Yeah. Okay. So here I have a hyperplane that is perpendicular to this, dual to this edge, and what I get is it must cross this orange hyperplane, right? Otherwise, those two will be connected, not separated by the blue. But what this means is that actually there is a square in here in which I see this crossing. Okay, so this is something for you to check. And what does it mean? It means I can shorten the green paths, right? So instead of it being this, I can now look at a shorter. So this is still a geodesic. Another color use often. This is still a geodesic. It's the same length. Okay, but now it has a shorter interval for which there is a problem. So I continue doing this until I get to a backtracking and I reduce the length. Okay, I think I'm out of time. Okay, so thanks.
Anyone want to add something quickly? For the last part of the what is there like a square near the? I mean,
why is there a square here?
Yeah, I mean the path above the hyperplane is like higher and the something just above the hyperplane.
Not sure I'm not sure I'm following it. We know that this thing separates this edge from this edge. Yeah. Okay, so it must cross the orange at some point. This is clear, okay. What's not clear maybe is why it has to happen in like an immediate square that you're just next to, right? That's the question. Why does that have to be exercised?
I see there is a square there, but maybe the path above is not touching the square.
Yeah, you're saying it could be that. I mean, the picture is I have the orange. And maybe somewhere they cross, but not immediately. Mm-hmm. Okay, exercise. No, it's a very good exercise. Yeah. Hint: the right angles. Okay, maybe I shouldn't say. Another exercise. I promise I'll mention this. Who asked me to mention this? Maybe Nima. You asked me. If you have a pairwise intercept, right? I'm just going to state it. Do you want to state it in yours and design this? It will be an exercise. I do want to say it. If I have a list of hyperplanes that pairwise intersect, then they intersect in a cube. So they all intersect. That's another exercise for the problem session.